it in a second here. Okay. All right. So here's what we have. Question number one, Chris, would be about motors, motor system. We have done that a couple of times now. Before I go ahead and I will give you, if it's too hard to read, Chris, I will give you this exactly like this, if you don't mind me. Later on, I'll print that one for you. Okay. Does everybody knows what we have here? We do have two motors sharing a feeders. One feeder, two motors sharing one feeder. So we have motor one, motor two. They're both running at 480. The full load AM for each one of them is 75, 90, 60 horsepower, 75 horsepower. Temperature rise 50, service factor 115, code letter L, code letter M, two of these motors. They're tied to a gutter with the top. They're all three-phase, obviously. They're tied through an overload, number 5, contactor, number 4, controller. Number 3 is overcome protection device fuse. Number 2 is a disconnect. Number 1 is the branch circuit. All the way into number 6, the overcome protection device for the feeder, and number 7, the feeder itself. We have done that many times, and this is just a quick review. Any question about what we're trying to achieve? We're trying to add 2 meters tied to a gutter to tie it to a system. Any question about what's given? Any question about what's given? Can I have thumbs up, Chad? We understand fully what's the requirement, what's need to be done. Now, if I have 100 motors like these guys, you do it the same way. 100, 200, same way, same calculation. Same way, same calculation. Now, Tom, my friend, you were showing me the other day the standard that you guys have where you work and how the size of the overcome protection device. I want you guys to pay a lot of attention about the size of the overcome protection device versus the size of the conductor for motors. Because you go to a lot of companies that have their own standards and they size the cables based on the overcome protection device. It's great if you're doing panels, awesome, that's the best way to do it. If you're doing motors, you almost always end up oversizing the conductor. If that's your company's work, no problem. That's the standard that they use. Otherwise, you might be able to save some copper as a contractor if you do the following. Okay, here's what I have, guys. I drew all this one to just expedite the process for all of us. So I have, and I do have the answers, but I want you guys to help me with it. So the following we need for M1, M2, we did that one before. The last column, guys, is the code requirement for all these sections. The first one is what the items that we want to find. And every time we have motors, based on what we do in the US, we always start with the full load current from NEC. Your start point always is full load current from NEC. So you're going to go to table 430.250. We went there many times and find the full load current for these motors. What type of motors do we have, guys? We do have 60 and 75 horsepower motors. They're both at 480. So when you go to the table, you're not going to find 480. You're going to find 460. Why? Because they rate them a little bit lower voltage, so they can handle if you have a low voltage in your line. They're not going to be grossly affected by it. Okay, so let's say if you guys go there, please correct me if I'm wrong here. This should be 77 amp, and this baby should be 96 amp. Can I have a thumbs up that, Chad, we know how to go to table 43250 based on the voltage and the horsepower and find the full load current? Yes, no? Based on table 250, 430, 250. Can you guys just find one of them? Make sure you know how to use the table. I have no doubt that you guys are great in finding that table. Okay, so that's basically the start point. 77, my 77, as well as my 77, as well as my 77 amp, as well as 96 for the two motors. Piece of cake. Piece of cake. Second thing is the disconnect. The disconnect. My disconnect is 430.20. Do we have no branch circuit? I have number 1 is a branch circuit. The only thing I want to change, this was from last year. We 430.22 here. So if you guys go to 430.22, and don't forget the table that got married, 310.15 B16. So that's changed because the table got changed. That's really not a big deal for it. If you guys go there, find the branch circuit. If you go there, it's continuous load 1.25. So Chris, you take the 1.25 multiplied by 77 And I did this one, and please correct me. This will be 96 here, 96 amp. If you go to this table, you're going to end up with 3 conductors, number 3. And if anybody, 3 conductors, number 3. 3 conductors, number 3, done. AWG, THHL. Please know how to go to the table and find continuous load. Second one, piece of cake. 1.25 multiplied by 96. You're going to end up, if I did it right, 120 amps. And that will translate into 3 conductors, number 3 conductors, number 1. 3 conductors, number 1. 3 conductors, number 1. Chris, are you coming with different numbers? Your calculator? Not plugging in? Okay. That's it. Straightforward. Now, tau, this is how we size the conductors. And later on, I want you guys to look at something. Piece of cake. We have done it a couple of times. This is the last time we're going to do it with Chad, guys, until the final. After this. Done. From here out to the industry. Okay? Disconnect. Number 2, guys, is a disconnect. The disconnect. Oh, come on. Number 2 is my disconnect. Let me go get my email out of whack here. Okay. Close email. So let's go directly to the disconnect. My disconnect is number 2. If you guys go to article 430.110, this is, believe it or not, 430.110. 430.110 DeWalt. Where's the DeWalt again? DeWalt 3-12. 3-12. You need to find the actual size. So we all know you talk about 1.15 times 77. If you guys did this one, you end up with 89 amps, and that will get you from DeWalt 100 amp. And then you go to the second one, 1.15, multiply it by 96. That will get you a healthy 110, and that will translate into 200 amp. 200 amp. That's done, right? Where did I get the 200 amp and 100 amp? Everybody knows how to go to DeWalt 3-12, guys. You have the standard disconnector there. Anybody need? Is the number right, Chris? Anybody can keep an eye on me? Yes. Cool. Okay. Really piece of cake. No gimmicks. Nothing. No gimmicks. Okay. Number 3 is the overcurrent protection device. For the overcurrent protection device, Jackson, I need to specify what type. There is non-time delay fuse, there are dual element time delay fuse, there are instantaneous, and there is inverse type circuit breakers. So can you guys read my chicken scratch here that says non-time delay fuse? What am I using here? Non-time delay fuse. If you go to table 430.52, it will tell you actually if you're using non-time delay fuse, right? Non-time delay fuse, your multiplier is 1.75. Your multiplier is it's 3. I'm glad one of us is awake. 3 times 77, and if you multiply 3 by 77, you're going to end up with 231 amp. And if you go to the next standard, the next standard will be 250 amp. My next standard will be 250 amp. Same thing, 3 multiplied by 96. If you guys go there, 288. The next standard will be 288. That will be 300 amp. 300 amp. Both of them, guys, if it's not a standard, you have to go up. On a branch circuit, where do we go if it's not standard? Up, not down. Now, tau, the sheet that you showed me for Hunt Electric, you know what they did on the branch circuit? They went down. Can I go down? Can I just get you to understand? Can I go down if I want to? Yes, please don't do it in the test because I need standardization in the test. When you go to your company, guys, if you find your company is going down on the overcurrent protection device, it's okay. It's not violation of the code. The maximum, we're talking about the maximum. The minimum, you can put any circuit breaker, but there's consequences for that one. So For the test, the code says go to next. For standardization purposes, we're going to go to the next standard. So if you went over here from 288 and you saw your company is going down to 250 on this type of motor, that's okay. For the test, can I get you guys to standardize so we can correct? Otherwise, it will be chaos. Okay, this is the fuse. This is my fuse. Now, some of you guys might ask, Chad, how am I going to fit a fuse 250 in a disconnect 100 amp? So we might have to, if this fuse is inside this disconnect, Chris, we're not going to talk about it. If this fuse is inside this disconnect, which it could be not. You know what I mean? If it's inside the disconnect, then what are you going to do with this disconnect? Up it to handle this. What's the next standard to handle this one? What is it? 300? 300. We're not going to go there, but these are things that you start thinking about if your fuse can't be fit in the disconnect, if they're both in the same enclosure. Sometimes they are not in the same enclosure. Same thing here. I have 300 amp fuse, 200 amp disconnect. How are they going to fit, Chad? You're going to go up this one to 400. Do we have 300 disconnect, guys? 300. I'm not going to go there, but just be aware of that. Controller. If you guys go to the controllers are a piece of cake. They size and best on the voltage. So 60 horsepower at 480. If you guys, this will get you a NEMA 4. And where do I get NEMA 4? This is 430.83, DeWalt 6-4. Is it still 6-4? I don't think they changed it this year. 6-4, right? So it will give you NEMA 4. Make sure you guys know how to use DeWalt 6-4. That's based on the voltage and the horsepower. It'll give you the NEMA size, the contactor. And this one, Chris's piece of cake, 75 horsepower at 480 volts, right? If you go there, it will get you the same thing, NEMA 4. Both of them are NEMA 4. Both these babies are NEMA 4. Can anybody verify that near NEMA 4? Everybody knows how to verify it from DeWalt 6-4. So tomorrow, guys, you're going to find an example exactly like this. For the test, do me a favor, Tao. Write the rules. I don't want to see an example. Write the rules, where to go, and all the stuff. I have no problem with that. I just don't want to see the example in front of me. Write with the rules, where to go to find things, all these here, where to go, fine, no problem with me. But I just don't want to see the example right in front of me. Okay, any question, guys, about the contactor? The contactor. Let's go to the overload. The overload, I want to remind you guys for the overload of two things. The overload are kind of weirdos. Overload, we have temperature rise of 50 here and service factor 115. The code says if the service factor is 115 or larger, the multiplier is 1.25. So you're going to see me doing 1.25 for number 2. If the service temperature rise is 50, so it's more than 40. If it's 40 or less, I do 1.25. Otherwise, I'm going to do 115. So please pay attention to the 50 and the 115 when it comes to the overload. Okay, so if you come over here, since that one has 50 temperature rise, it becomes the multiplier 1.15. Where do you find this info? 430.32. Multiplied by the full load amp. You have to multiply it by full load amp, guys. In this case, which is 75. 75. That's the most important thing. 75 is a full load amp. And you end up with 86, I believe. 86 amps, leave them as is. The second motor, guys, have a service factor 115. Where did the 75 come? The 75, guys, for overload, we always multiply the full load amp. The full load amp on the nameplate. The full load amp on the nameplate. Please write to yourself a note. Full load amp on the nameplate, always used for overload. Overload only. Cool? So here's my 75. The second one, because the service factor of number 2, guys, is 115, so the multiplier is 1.25 multiplied by this. That motor number 2 is 90 amp, and from here equal 113 amp. 113 amp. How many 13 amps?
That 75 is not a full load.
This full load amp from the nameplate.
Oh, okay.
From the nameplate. Given. Only for the overload, guys, we always use a nameplate. Everything else, you use the code NEC code letter, which is the one that we calculated right here, right? Right here, the top, full load current. Only for overload, or if you say here, name plate full load amp. Please write yourself a note right here. Name plate full load amp.
Device is that you're calculating the circuit breaker?
We're calculating the overload, that little device here.
Oh, okay, for the motor.
Yeah, for the motor controller, the overload. Number 5, we're calculating, guys, this baby here. Number 5 is right here, the overload. Number 5. I know my love. The fuses are for the short circuit. When we have motors, we calculate short circuit. We have devices to protect from short circuit and ground faults, and we have devices to protect from overload. Okay? Okay, short circuit. To find the short circuit, guys, for this the last one would be start current. Let me just erase that one and write it properly. Start current. The starting current for these systems, guys, the starting current for these systems, I start equal, you're going to go to table 430.7b. From 430.7b, guys, you need to find the multiplier. The multiplier here is 9.99. Multiply it by how many horsepower we have? 60. Multiply it by 1,000. Divided by the voltage, which is 1.73 times 480. If you did all this, you should end up with 722 amps, Chris. 722 amps. The calculation for this. If you do the second one, 11.19. If you multiply it by the horsepower is 75 for this one, multiplied by 1,000, divide by 1.73 times the voltage is 480. If you do this for that baby, you're going to end up, oh boy, yeah, read it. 10, 11. Can anybody verify that one? 10, 11 amps. Anybody can verify that one, guys? 10, 11. Please verify it. Yes, sir.
What is the difference between the gold letter added two together, you run the upper one?
Always the upper one. The worst scenario is the upper one.
Find the average. That's what they use.
Yeah. Use the worst scenario. The upper. There's methods. For the test, use the upper is the worst scenario. Use the worst scenario. Any question, guys, about this? That's it. Let's go find the feeder. Find a few things for the feeder. Any question? A lot of people, I see your point. When you average them and find the average or find the mean or median, there's different ways of doing it. To standardize for us, guys, we're going to take the worst scenario. We're engineers. We can do anything we want. Standardize, take the worst scenario and size based on it, unless we know otherwise. Let me know, guys, when you're done so I can move to the feeder. And then I'll give you a quick break here. Cool? Okay. Let's go get the feeder. The second thing, guys, I need the feeder overcurrent protection device. The feeder overcurrent protection device, Chris, you take the 300 amp largest, fattest fuse, add to it 77 amps, you end up with 377. And if it's not a standard, you have to go down to 350 amps. So your overcurrent protection device have to be this amount or lower, the maximum overcomputation device. Where's the 300 came to be? That's the largest fuse in your system, right? Then you add to it the full load current of the second motor, and that will get you, of the second motor, and that will get you this number. You go down. The feeder, guys, the feeder conductor, you take 1.25, multiply this one by the largest, fattest motor, which is 96, plus, see where the multiplication goes, plus 77. If you do that, you're going to end up with 197 amp. And if you go to table 310.15 B16, right, under 75-degree column, you're going to end up with 3 conductors. Each one of them is 3 odd as your calculation. Any question, guys, about finding the feeder and the overcomputation device for the feeder? The feeder and the overcomputation device for the feeder. Now, this is for my friend Tao. Now, imagine, Tao, take this. Some people, guys, come, look, Chris, we size the feeder based on 197. What you were showing me the other day, that sheet, they size it instead of 197, they match it to the overcomputation device, 350. Can you guys see the difference between 197 and 350? Major difference in terms of amps. If you do 350, your conductor here, Chris, probably 500 kcm. We went from 500 kcm to 3 odd. Major difference. And there is a reason why they do this, guys. Sometimes some companies, for example, if this feeder was the feeder of a panel, definitely we do that. You know, we match for the panel, we match the overcomputation device, because the future, we don't know what they're going to be adding in the future into this panel. But if it's just a feeder tabbed like we did, guys, and I know I'm not going to add to this feeder in the future, it's a good idea to size it based on the code, the minimum. Everything that we did, guys, in terms of conductor is minimum, in terms of overcomputation device is maximum. Yes, sir. Go back. Sorry for that.
Okay, you got these things numbered.
This is 1, 2, 3, 4, 5.
Start current is 6.
No, the starting current I didn't number. Just the next one. I did not number the start current. Number 6, Chris, is right here. Here's where I put number 6. Number 6 is the feeder, and number 7 is, because start current is not something that we
really size.
We don't size, but we have to be aware of it when we set the relay. Not the relay, when we set the circuit breaker, or we do coordination and so forth. So it comes handy. Very good question. Why would they worry about start current? That's what Chris is asking me. Start current, guys, comes very handy when I when I look at the overcomputation device coordination later on. Just FYI. Okay. You guys want a 5 minutes break before I move into the next one? Okay, let's take 5 minutes break and we'll move into HVAC equipment. Rob, good? Thanks, sir.
Step 7.
Give me 1 second, Aladibo. Step 7, okay. Do I have step 7? Where? Do I?
He's got stuff.
Am I mismatching here? Oh, 7 is a feeder. I got it, Aladibo, here. Yeah. Oh, you just won't look at it. I'm sorry. Okay. Did we do anything wrong in the calculation, Chris? Check it, will you? Okay. Equipment. Question number 2 tomorrow, guys, will be about HVAC equipment. What you're looking at, Rob, my friend, is a 480 system. Same thing. Tomorrow could be 208. No difference. No difference. No. I have two AC units, could be chillers, anything that has a compressor in it. This applies for Article 440, anything that has a compressor in it. Two ACs, the full load amp on the nameplate, Chris, these have compressor with them, so a special type of motors. Apply different rules. 750, 75, and 60. The locked rotor current is also given to me. You're going to know why I have the locked rotor current at 3-phase. And we are supposed to size the branch circuit. Number 1 is the branch circuit that goes to AC1. And then, of course, AC2 has its own. Number 2 is the overcap protection device. Number 3 is the disconnect, branch circuit disconnect. Number 4, the feeder overcap protection device. Number 5 is the disconnect for the whole system. And number 6 is the feeder for the whole system. Can I have thumbs up to know that we fully understand what we're looking at here, the one-line diagram? Guys, being engineers and designers, this is our start point is always called a riser or a one-line diagram. What you're looking at is a one-line diagram of the system, how the system is put together. And then we're supposed to fill the information, give it to the electrician, they go install it, right?
What's number 6, Ken?
Number 6 is should be the feeder that's coming in here, right here. Thank you. It's shifted a little bit. The feeder that's coming in. Okay. Now Chris is gonna redraw this one in a really nice format. All right, let's go to the following, guys. A couple of things, guys, that we need to adhere to. So number 1 was my branch circuit. If you guys go to 440.22, 440.32, and this is actually changed slightly, so let me just go directly into here. Let's use red again. 440.32, Chad, right? 440 for this system was .32, yep, .32. And also don't forget the table, 310.15 B16. These are what the rules that you need to apply. Piece of cake. If you guys go there, it will tell you the conductor is 1.25 times the full load amp, which is 75, and that will get you a healthy 94. And if you go to the code, you're going to have 3 conductors, number 3, done. Second one, same thing, 1.25 multiplied by the full load amp of that baby was 60, right? 60, yep, 60. And math should be, if you go there, 75 amp, and then you go to the code, that will give you 3 conductors, number 4, done. 3 conductors, number 4. Any questions? Straightforward, 1.25. Continuous current. Any question about this, guys? No gimmicks, nothing, like any other motor. Now the overcap protection device, Chris, overcap protection device, care less if it's fuse or disconnect for the sake of the calculation. Here, they care less if it's fuse or disconnect. I mean, if it's fuse or circuit breaker, what type of fuse, they really don't care. The only thing they tell you, if you go to Article 440.22, if you go there, it will tell you, start with 1.75. If your system doesn't start, multiply by 1.25, or 2.25. So I'm going to start with 2.25 this time, assuming the system is not going to start. Okay? And I know I've done it differently another time, 1.75, but if you read it, guys, it tells you if it doesn't start, go to 2.25. Let's assume the worst scenario, 2.25, multiply it by the same thing, 75, and if you guys go there, it will give you 169, and that will translate into a healthy down 150 amp. And you go down, don't forget the down. This one is the same thing, 2.25 multiplied by 60. That will get you 135. You go down to 125 amp, done. Yes, sir. On the test, if you do it this way, but if you decided to be a smart aleck like Chad, and you put 1.75, Chad, I assume I'm going to use 1.75 from the code, and you size it, I will give you full credit too. So, you know what it says.
Okay. So you can go up to 2.
If you know the equipment is not going to start with 1.75, you can go up to 2.25. If you read through it. Yeah. So it's up to you guys where you put your start point. I'm gonna put, you know what? Can I admit one little thing? These guys will be sized by the manufacturers anyway. Remember how we said this is a maximum overcam protection device that's sized by the manufacturer. So you're gonna find it sized by the manufacturer anyway. But for the sake of knowing how, for the test, size it, boys, on 2.25. Cool? That's why I put the article there, because somebody like Aladibo wants to go challenge, I'm going to go 1.25. That's fine with me, Aladibo.
Take it out in the parking lot.
We'll take it out in the parking lot, huh? Okay, disconnects. For the disconnect, guys, there are two methods of doing for disconnect. Can I get you guys to pay attention when it comes to the disconnect? Because electricians are smart, global people, and they can come to a motor that's plugged in with a disconnect like this, while the AC equipment is running, somebody could go and open the circuit via the disconnect. You're not supposed to do that to de-energize the circuit. You're supposed to use the controller to de-energize the circuit. Because of this, guys, they want the disconnect to be able to do, to handle the amount of current interrupted by the disconnect. So who cares? They do two sizes to make sure that it will account for mistakenly somebody disconnect the motor via the disconnect. You're not supposed to do that. The disconnect is supposed to de-energize the equipment. Now it's dead. Go. Then you go disconnect it, lock it, tag it, and work it. Isolation. Okay, because of this, they have two sizes for them.
It's meant for isolation, but it can be used in emergency
It's not supposed to emergency. You're supposed to have a push button like this to energize the system. Mushroom head button, you hit the energize. That's your emergency push button. And you see how you have to activate it. You physically, mechanically have to open it. So that's your emergency.
So we're gonna rate it though, just in case.
Just in case somebody de-energizes the equipment. There's a switch there. You see a fire and somebody panic, instead of going to the push button, they can de-energize that one. Okay, it handles it. Because of this, if you guys go to 440.12 and DeWalt 312, you guys are familiar with this one. 1.15, that magic 1.5. 1.15 multiplied, Chris, by the same 75. That will give me 1.15. That will give me what? That will give me 86 amp, and this will translate into 100 amp from DeWalt, and 1.15 again times 60. That will get me 69 amp, and that will translate also to 100 amp disconnect. Both of them amp wise, they will be connected. They will be sized as a disconnect. Okay, this is easy. This is very easy to remember and do. The second two are kind of a tricky. The second two, guys, you have to size horsepower. This is the amp size. We know what the amp size is. Now the horsepower, the energy size. The horsepower, you go to two locations. One is full load amp. Believe it or not, this is a full load amp. So you're going to size two things based on, I hate it when it becomes full load amp, okay? And the second one is locked rotor current. Very easy. I just want to remind you, you're going to go to table 430.250 and 430.251 for each one of them. Look how they do it, guys. Take the first one. What's the full load amp of this guy? Was 75. If you guys take it to table 250, what does it translate to in terms of horsepower? 60. It translates to 60 horsepower. So this will give me 60 horsepower. Same thing for the other baby. 60 amp. These are amps. If you take it to 430.250 under 480, it translates into, Chris, 50 horsepower. So that's how you translate from, because I don't know what the horsepower rating for this disconnect, right? I don't have a horsepower for these equipments. So based on the full load amp, Chris, you can find actually the full load amp, you can find the horsepower. Now horsepower 1. The second horsepower that you need to size is, guys, based on the locked rotor current. The locked rotor current for this one is 400 amp. If you go to table 250.51b, this will translate also to 60 horsepower, believe it or not. And the second one is 360 amp. If you go to 430.251b, this will also translate into 50 horsepower. So Nick, can you choose between which is the largest, 50 or 50?
51.1.
That's smart, Alec, question, huh?
Yes, and I have started.
So you pick, so you pick the largest of the two. Does that make sense? If that was 50 and that one was 60, you choose, of course, the largest. So for AC number 1, both of them got me 60. For AC number 2, both of them got me 50, Chris. So it's 50. But can I get you guys that we have to choose the largest of the two? So Ashley, when you go to Warner Electric and order you disconnect for this equipment, you're going to say, I need 100, a 3-phase, first of all, 3-phase, 100 amp, 480, disconnect rated for 60 volt, 60 horsepower, and the other one rated for 50. Now, William, they might not make 50, 100 at 50. They might jump immediately 100 to 60. So can I use 100 horsepower, 100 amp guys, 60 horsepower rated to disconnect this thing? Yeah, no problem. It's just overrated more than a little bit more. So can I guys get you to understand? You could, to standardize, Nick, you can go order this one, which is 100 amp, 60 horsepower, disconnect 480 for both of them, right? Right? Because it's 100, here's good. This is 50. I am asking for maximum of 50, minimum of 50, but I add 60, so it's stronger. Any question, guys? Okay, so besides the disconnect, number 4 is the feeder overcome protection device. The feeder overcome protection device, Chris, is piece of cake in terms of feeder overcome protection.
Just one question, Chad.
Yeah, go ahead.
I'm looking at the table 430.251b.
Uh-huh.
Did you just round the
You go next, like if there's no 400, you go to the next 450 for whatever.
Oh, okay.
You go up.
260. Is that in DeWalt then?
This table should be in the wall too.
Oh,
Should be in the wall.
so that's how you.
Yep, that's how we get the horsepower rating for the equipment. Okay. Any other questions, guys, before I move into the feeder overcome protection device? Number 4 is the feeder overcome protection device. Ashley, like any other feeder, you take the largest, fattest, fluffiest fuse, which is this fuse, the largest, fattiest, fluffiest fuse, like any other motor, plus the full load amp of the other babies, right? And that will give you, if you do the math here, that will give you 210. That'll give you 210. And if it's not a standard, guess what you're going to do? You're going to go down. You're going to go to 440.22b1 and 240.6. You guys know how to find the standards. So the next standard down is what? 200 amp. So my fuse is going to be 200 amp for the feeder. For the feeder. For the feeder. Okay? Did they do it wrong? 210, right? And then you go down. You don't go up, you go down. That's the feeder. That's right here. The overcome protection device. That's the feeder overcome protection device, right here, number 4.
And that's in 440.
That's in 440.22, I think. 440.22b1. Okay. Any comments, any questions? Similar to the motors with a smash with some. Now, press this, you have to size. Okay, can I go back? Can I get you guys when you were here? Remember when we talked overcome protection device right here? Number 2 is actually called the maximum overcurrent by the manufacturer provided. And the number 1 and number 2 are always provided by the manufacturer, almost always. This is called minimum circuit amplicity, and this is maximum overcurrent protection. These two are provided by manufacturers, the first and the second. If they are not, this is how we do it. Okay, let's go to feeder disconnect. Feeder disconnect. The feeder disconnect, guys, we're going to size the feeder disconnect in terms of amps. And so let's use this one. The feeder disconnect, the amp size of the feeder disconnect. Here's what they say. You take 1.15, and I can't emphasize, it's strange, not strange, but, and then you multiply by all, 750, 75 plus 60. Okay, you can see how you multiply by the sum of the two. Multiply by the sum of the two, and that will get you 155 amp. And if you go to DeWalt, that will translate into 200 amp. For 40.12b, DeWalt 312. You multiply by both. You add them up and you multiply by both. That's the amp size. Now remember, disconnect, guys, you have two sizes for it. There's an amp size and a horsepower size. The amp size, piece of cake. We done it. Piece of cake, right? Now the disconnect size, the horsepower size. So this is number 5 amp size. Number 5 disconnect horsepower size. We do two calculations and we choose the largest. So let's do that. So from the full load amp press, the full load amp of the first one is 75 plus the full load amp of the second one is 60. Add these up to 135 amp. Okay? Then you take the 135 amp, take it to table 430.251b. I'm sorry, 430.250 because it's full load amp. This will translate into 125 horsepower equivalent. Let me repeat myself. You add the two full load amps, 135. Take the 135 to table 430.250 under 480. That will translate into 125 horsepower. So that's the first horsepower rating. Let's go to the second horsepower rating. The second horsepower rating, guys, is locked rotor current. Locked rotor current, I have 400 given plus 360 press. That will translate into 760 amp. Take it to table 440.33. 430.33. I'm sorry, you're going to take it to this table. 430.251b, and that will translate again into 125. Oops, let's write it in red. 125 horsepower. So this 125 horsepower. So William, we need to choose the largest between 125 and 125. Can you help us here? So I have to pick one. So we're going to choose the largest. Obviously, they're the same. So we hit the jackpot basically here. Otherwise, in your case, if these were different, guys, I want you to highlight the one that's the largest and say the disconnect will be the largest horsepower plus the amps. So
How did you get from the 135 to 125 on the, you have the full load current added up to 135 amps.
Yep.
And you go look that up.
You look it under 430.250,
Okay.
under the voltage 480,
Yeah.
amp wise, translate to horsepower. It's kind of reverse function. Instead of having the horsepower find the full load current now, we're doing a full load amp, reversing it into the horsepower. Reverse function. Same thing, guys. These two are, we're used to actually having a horsepower and a voltage finding the full load current. This is the opposite. I have a full load current. I need to find the horsepower. So if 135 is not a standard, what do you need to do? So you have to go next, right? The last thing in this system, guys, before I switch is 1.25. The feeder conductor, piece of cake, 1.25. Multiply this baby by 75, the largest, fattest, fluffiest motor, plus the full load amp of the others. That will translate into 154 amp. Take this one to 3. This got another change here name from last year. So this has become stable 310.15B16. If you guys go there, it will give you 3 conductors, number 2 aught. Have you guys noticed that I use 3 conductors all the time with equipment? The default is 3. Unless you know they need a neutral, you always default to 3. Why 3? 3 phase. That's piece of cake. And that will be the first sheet, guys, before I switch to the second sheet. You know that one? You is the test tomorrow. Really, no gimmicks, nothing. Let me know when you guys are done so I can flip to the second part. The second part, guys, have very easy symbol. Has 2 things that we need to size, Chris. A UPS PDU system and a panel transformer combo. Let me know when you're done with this. I can't emphasize, guys, there's another example on YouTube, exactly what we have done, if anybody wants to go fuck around with it. But if you do that, this is a quick review for you for the test tomorrow, piece of cake. You follow all these, multiplied by this and that. Dustin, I know there's so many multipliers, so many things. Write it down, guys. Write it down. Write it down on a piece of paper, your cheat sheet. Otherwise, it's almost impossible. We're designers. If you have all the information in front of you, you should be able to do your work. So, Alaribo, can I move to the next one? Okay, thank you. Let me save so I can't screw up this. Okay, Chris, take this. I have, this is a UPS system. This is a UPS system. And you guys are sizing a UPS system. The following, you need to understand about, those of you who were here when we did a UPS system, this is very similar. The first thing you need to understand about the UPS system, I have a data center. The power density is given as 90. I'm giving you power density of 90. System is 480. I need a power factor of 80, and the area of the data center is 45 by 45, square room, by 45 by 45. And I'm assuming a losses of 10. I have a losses, I gave you a losses of 10 here. Do me a favor, I used to do 10 here. Can you just change this one to losses to 25%, okay? Change this one to 25, will you? Way at the top, 25. To accommodate for all the losses in my system, 25. 25%. Way at the top. Okay, so what do I need to do? I need to come up, you guys are familiar with the 480. The UPS system, take a 480 system, convert it into DC, typically 660 volt DC, tie it to the batteries, come out of the batteries with AC, invert it at 480, dump it at a PDU. The PDU has a transformer inside it. From the transformer, there's also a panel with a transformer in the same box. And from there, you can feed all your electronic equipment. These are all electronic equipment. Our system that I want you guys to size is 2 PDUs. So I have my computer here, my server, and it's fit from 20 amp. I have a 20 amp circuit feeding it from both panels. Here's a 20 amp and a 20 amp. This is just to get you how the system how it works. PDU 1, PDU 2, you guys are doing it with us, right? On the manufacturing floor. I think everybody understands how the UPS system. Who cares? Why do we do a system like this, guys? Because actually, on the DC level right here, guys, you are always tied. The power is, you have 2 sources of power tied, synchronized at all times. So if you were to lose this side, you don't have to switch. The battery here will take care of business for 15, 20 minutes. So you would never see any interruption in the power. Cool? That's why they have the UPS system. Any question, guys, about how the UPS system works? almost this thing is a UPS is one big fat box where you have a converter to DC, an inverter back to AC. At the DC level, they tie the batteries. I don't want to get you through sizing the DC guys system because you need to know what the size of the batteries and all this stuff. We're not going to get into that branch here. We're only concerned about the AC part.
How are the batteries being charged?
Oh, there's a charger, and yeah, I'm not showing. This is, yeah, there's a charger. There's a few other systems. This is just a skeleton one like that. Absolutely, you need a charger. You need to charge it. Yeah. Yeah. I give you two.
I didn't see it.
Can anybody guess? There you go. Thank you. No problem. So somewhere in the DC level here, it will be charging your batteries at all times. Okay. So what do we need to do? We did this one before, guys. Number one, I need to size the UPS. Number two, the overcome protection device for the UPS. Number three is the feeder for the UPS. Number four is a PDU. Number five is overcome protection device for the PDU. And number six is the feeder that's going to the PDU. Any question about how the riser is put together? What we need to size? Right? So basically the PDU and the UPS, the feeder to the PDU and the feeder to the UPS, the overcome protection device to the PDU and the overcome protection device to the PDS. PDU and the UPS. PDU stands for power distribution units, nothing other than a fancy name for a big transformer and a 281 23-phase panel in the same enclosure. That's it. That's what a PDU is. Because a panel is just typically a panel has no transformer in it, unless it's a substation, they call it. If you put a transformer inside the panel, it becomes, they call it power distribution unit. One name for it. Okay, any question guys about this, the system? Let's go size. Okay, so, I'm sorry. Yes, the supply, that's why we have a transformer. Typically, this is very typical, Chris. Typically, that side will be 208, 120. I'm not aware of any side where you feed the server themselves at like 480 in the US. I'm sure somewhere else in the world they feed them at 230. So, but I've never heard or seen a server. I'm sure it's there where you feed it 480. Yeah, or 277. Okay, the first thing that we need to do, guys, is that little formula that I gave you. A lot of these are opinion, guys, so there is no code reference to it. Find the KVA. KVA for the UPS. I told you this square foot multiplied by density multiplied by 1.25. That's for the losses and all this good stuff. And power factor, and divide by the power factor and by 1,000. If you guys plug in this in your formula, you plug in all this good stuff. So I have a 40 times 45, 45 times 45, that's the area, multiplied by the power density is 90 multiplied by 1.25, accommodate for losses in the whole system. I know it might be exaggerated a little bit. Power factor 0.8, multiply this by 1,000 to convert into kVA. When you do all this math, you're going to end up with, I believe, 280. If you do this, you're going to end up here equal 285 kVA. Okay? Now you're going to take this one. You're going to take this one to the wall. You guys, I asked you to write these, right? If you remember, or the sheet that I gave you. Did you guys write them here, or do you have a sheet for them? I wrote them. I asked you to write them in DeWalt 3-13. 3-13. If you don't have it, it's not in the book. You guys, I asked you to write them in the book. And the next standard for us from here is 285. It's 300. The next size is 300. Again, these are for Ashley. These are for practical reasons to do the calculation. If you go to different manufacturer, they might have a different sizes in between. So, for example, 285, they might have 290. So you use a 290. But just to standardize, so we can do some calculation. This is close to the truth, but might not be all the truth here. So my size is 300 kVA. So I'm going to go buy a UPS, 300 kVA UPS. Okay, any questions about this? So tomorrow, Nick, can you get this formula with you, the top formula that we did? Okay, if you guys need so you can substantiate my opinion here, I'm going to get you an article 645.25. 645.25. This is typically where if you go there, it'll tell you under engineering supervision, you can do anything you want. And that's what we're doing. You know, under engineering supervision, that's how you calculate it. Okay, 645.25. Okay, let's go to the UPS overcome protection device. The UPS overcome protection device, my friend, UPS overcome protection device. This becomes piece of cake. You take the I. Now we need to calculate the current. 300K divided by the voltage is 1.73 times 480 because of 3 phase. If you guys go there, we'll get you a 361 amps. And then I need to multiply this one as a continuous load. So that's step 1. I want to treat it as a continuous load and take 1.25 multiplied by 361, and that will get me continuous load 452 amps. And actually, if you take the last one is if you take 452 amps, take it to 240.6 to find the standard, and that will get you 500 amp, and go up if it's not a standard.
The last time around, you said it had to be less than or equal to the available sizes. The last time we went through this.
This one? Or which one?
Number 2 here.
This, or this or equal. Not go up. Well, up to 800 amp. Remember that the ceiling 800 amp. We can go up on the conductors. After that, you're absolutely right. After that, we have to match the overcome protection device to the conductor. Yes, sir.
On the size of the UPS, we did the continuous 4.25.
Really, that first one was mostly for opinion. Again, let me just say an opinion. It's for losses, to accommodate for the losses in the system, because you're converting AC to DC and missing all this stuff. So we're upping it 25% to cover our butts, basically. The rest is continuous. That's where I get my continuous on the overcome protection device. Okay, so that's my. Any question? Good ones. Any question, guys? So we got my continuous here. UPS conductors. My UPS conductors, guys. Here's how I cover my butt, Chris. For the conductors, the UPS, I would say UPS conductors match overcurrent protection device. Or up to 800 amp, you can use 1.25. But after 800 amp, you have to match the overcurrent protection device. So I have a 500, remember that 500 amp, divide by 2 because I want the parallel. That will give me 250. Take this one to table 310.15 B16 under 75-degree column, and that will get me the following, Ashley. That'll give me two sets of how many conductors of, now coming into the switch gear, I don't need a neutral, 3 conductors of 250 kcm. This is one way of sizing it. Can I carry, may I pull a conductor 500 kcm? You can. As I said, after you go higher than 400 amp, it's a good idea to start paralleling. Remember that cutoff, 500 kcm or 400 amp? good cutoff to do sizing. Okay, now PDU 1 and 2. I said same size, guys, as as UPS. The same way we size it. I'm not going to repeat the steps. Same way like the UPS. So you're going to get same calculation, same sizing. Everything is the same, and we have two of them for redundancy. So we're going to size them 100%. Both of them are going to be the same size for what? Redundancy. Remember how if one of them fails, you shift the load to the other one. So if you guys take the size, how did we size the UPS? We 280. We did all the calculation. We came up to 285. I'm going to start by the same size in this case. Well, 285 kVA, and I went to the DeWalt 3-13, was it? 3-13, where I asked you to put them, came up with 300 kVA. I don't want to repeat all the steps, the same calculation. Okay. $300 kVA. I'm sorry, audible? Same calculation. We did the same calculation like we did for the UPS, yeah? I just don't want to repeat it. When I say the same calculation, gears, we did the same rule here. Yeah, the same size, same came up with 300 kVA. You can use the same calculation, Chad. Yep, that's fine. Okay. The second thing, guys, is the overcome protection device. If you overcome protection device, since the PDU guys have a transformer inside it, right? The PDU has a transformer inside it. We size it slightly different. So this is coming 450.3B, 450.3B here, 450.3B. If you go there, it tells you 2.5. So you take the on the secondary side, 2.5 times, what's the full load amp of that transformer? I'm just going to start by, first of all, finding the I equal 361. This is I for the PDU, guys, right? PDU. How do you find I for the PDU? Take the 100 kVA, the 300 kVA divided by the voltage, okay? Then from there, you take the 2.5, so that's step one. Step two, 2.5 multiply this by 361. That will get me 903 amps. You have to go down because it doesn't allow you to go up. Then 903 amps, take this one to 240.6, and that will give you a healthy 800 amp. A healthy 800 amp. Or less, or less. Now, if you go and find the manufacturer guys put 700 amp, is that wrong? No, or less. Conductors for the PDU, the same thing, guys. 1.25. Multiply this one by 361. Same calculation. 452 amps. And then I'm on the parallel. 452 divided by 2 equal PDU conductors. Did I find the PDU conductors? Coming to the PDU, that will get me, if I parallel to 226 amp. If you go there, that will get you 310, based on 310.15 B16, 75-degree column. That will get you 3 conductors, number 4 aught, And how many sets? Two sets of 3 conductors, number 4 on.
Ken, where did you get the 361?
361 is the amp, guys, for the PDUs, which is the same as the amp for the UPS, right? The same size.
The UPS was
300 divided by the voltage. This is the amp for the PDU on the primary side, this amp. This is coming, guys, from 300K divided by 1.73 times 480. Cool? Can you write this? Because if you take 300 kVA divided by 1.73, 480, get you 361. Based on the 361, you size the conductor and the overcap protection device on the primary side. Now the question would be, Ashley, what happened to the secondary side, Chad? What happened to my secondary side? My secondary side, guys, let's go back here. Go back again. I'll be back. Can you guys see the secondary side here? Is there a secondary side? The transformer is completely bussed into the panel. They're bussed to each other. So I don't have any secondary here. Right? They're bussed together. Meaning it's sized by the manufacturer. So, Nick, what I was sizing is just the overcap protection device and the feeder, these two, typically. Okay, let me go, guys, back into a lot of people. Did they went too fast, bud? Okay, let's go here. Okay, any question, guys, about this? Any question about this? Done with the PDU. The last example that I have for you. The last example. Are you done with this? Is panels. Matching a panel. Now this is industrial building, and I have the following. And I did the calculation. Did I copy all this for you guys? You need to do this tomorrow. I copy this. First, we're in actually any building. It doesn't have to be industrial. And I have a transformer and a panel for the receptacles. The primary is 480. The secondary is 208. I need a feeder from the transformer to the 208 receptacle panel. And I need a feeder to feed the transformer, overcap protection device for the transformer, and so forth. So I need to size the following. Number 1, the transformer. Number 2, the overcap protection device on the primary. Number 3, the feeder on the primary of the transformer. Number 4, the panel on the secondary. Number 5, the overcap protection device for the panel. And number 6, the conductor that goes into that panel. This is typical transformer receptacle panel. Every building they get into, guys, you're going to have this type of scenario, like we say. A transformer that feeds the receptacle panel. Why? Because we burn our receptacles in the US at 208. So you have to have transformers. Okay, now, please be aware of this one. This is a receptacle panel. So I assigned that my friend Rob, and he put 440 kVA load of receptacles, 444 kVA, and I need to find the demand. This is just receptacle load. Basically, you took 180 multiplied by how many receptacle, you came up with 444 kVA. I need to demand them. Everybody knows how to demand it. The first 10K from 220.44, the first 10K, leave them alone. Anything higher than 10, cut it by half and add. Don't forget the word add. Any question, guys, about this slide? So the number that I came up, 27 kVA, is the demanded load for the receptacle. Demanded. They call it demanded. What's demanded versus connected? This number here, guys, is called connected load. Connected load is just all these receptacles added together. Demanded load is taking into consideration that it's highly unlikely that all of them are plugged in and sucking 180 volt amp out of the system as we assumed. So we demand them. Can I get you guys to understand the stuff in the red here? How I demanded this load? You're going to do it tomorrow, you're going to do the same thing. I'll give you a value like this. If it says demand, leave it alone. If it says connected, then you have to demand it. If in doubt, ask me. Say, Chad, is this demanded or do I need to demand it? If you need to demand it, you need to do this step here. Basically, if it's already demanded, you jump directly into the sizing the transformer. Okay, any question guys about this? So I need 27 kVA worth of power to feed my receptacles. That's all what you care about. Cool? Okay, so we go to the receptacles. Now I'm going to go directly and size my receptacles. So remember that 27 kVA, the demand load. Based on the demand load, guys, you're going to go to DeWalt 7-7, Chris, 7-7.
Yeah,
And you're going to go, what's the next standard?
30.
30 kVA. And I hope you guys know how to use that. Yes, sir. Phil?
44 minus 10 is 34 times 0.5, I'm getting 70.
Did you add the 10?
Oh, I think.
Yeah, add the 10. Yeah. Add the 10. 10, add the 10. Right? Okay, no problem. Okay, so this is my actual size of a transformer. That's it. So I need 30 kVA transformer. Everybody got that? All right, so we found number one, the size. Oops, why am I in a hurry here, Chad? Number one is the size. Let's go to number two. I need the primary overcome protection device. The primary overcome protection device number two, guys, is basically I primary equal, I have a 30K divided by 1.73. The primary voltage is 480, right, Chris? 480. You're going to end up with 36 amps. And Nick, you can find the actually from the table that you guys have. It will tell you what the full load amp from these tables, 36 amps. Okay, if you guys go to 450.3b, we'll tell you you can multiply it with 2.5. So step number one, step number two, 2.5 times 36. Where did the 2.5 came to be? From 450.3b, right? Everybody can see that multiplier coming right from here. Okay. You do your math on this baby, get you 90 amps, and then the last thing you need to do is you take the 90 amps, take it to 240.6. If it's not a standard, what do you need to do? You need to go to the next standard down. So we happen to have a full standard, so we don't need to worry about that one. 90 amps. If it was, actually if it was 94, you can't go up, you have to go down. 90. Primary conductors, same thing for primary I. You take IP equal, guys, 36 amps, right? Now, this is one. Number two, I want to assume continuous load 1.25 times 60. I'm assuming I'm taking the full load amp out of this transformer continuously. That's my assumption. Reasonable assumption, though. I used to size based on 36, but it's a good idea to size based on people. You allow him to use the full capacity of that transformer. Okay, I think 45, Chris, 45 amp. And if you take the 45 amps, take it to table 310.15 B16 under 75-degree column. Why 75 even though it's 45 amps? Three-phase equipment, the logs almost always are rated for 75-degree column. We know that, so we size based on this. Okay, so if you guys go there, I believe, what did he?
You said we should go down.
Yes. Because if you go 450.3b, there's no note number one. Remember we talked about note number one on the table? There's no note number one that tells you to go down. On the primary, it to go up on the primary. On the secondary, it does. Not on the primary. Okay, so what's the conductor? Chris, I have 3 number 6, right? 3 number 6, AWG. Now the question is, why not 4? We're bringing delta transformer, guys. Most likely it's going to be delta on the primary. 3 conductors. I don't need a neutral on the primary side. Now, tau, if you go to Hunt Electric and they're using number 1 here, is that wrong? No. Voltage drop, longer distances. That's the minimum, the bare minimum. So if you see a number bigger than that one, guys, don't sweat it too hard.
Should it be number 8?
Is it? Did I, is it number 8? Okay, thank you. The minimum. I'm going by the minimum. So it should be number 8. Again, minimum. If you find number 6 or higher than that, not a big deal. But bare minimum, directly from 75, right? Number 8, the bare minimum. You highly unlikely, guys, you're going to find number 8. Probably they put number 6 or higher just because of voltage drop or whatever. Okay, so that's a primary conductor. Can I move to the second one? Yes, no? Okay, the panel size. Now let's go to the panel size, my friends. So for my panel size, here's what I do for the panel size. The first thing you need to do is find the I secondary equal 30K, divide this baby by 1.73 times 208 this time. Now because we moved to the secondary size, that will give me 83 amps. If you take step number 2 is to take the 83 amps, multiply them by 1.25 because I will accommodate for continuous load in this panel, and that will give me 104 amps. And the last step, guys, is to take the 104 amps, take him to D Walt 3-12, and what's the standard panel that we need to buy? 125 amp, a 3-phase 125 amp panel. This is the size of the copper or aluminum inside the panel, not the overcap protection device. That's just the size of the panel. Now, later on, you guys, the code say the size of the panel is the size of the overcap protection device that protects the panel. But we are engineers, we need to buy the panel first. And then we put the overcap protection device. It's up to me to get it. So I size the panel 125. The reason why I do it this way, Tao, because later on when they do value engineering, you might find a panel that's 100, say a 400 amp panel, and the overcap protection device is really 200 or 250. So you might have to value engineer and say, you know what, I can get away with 300 amp panel size to have a cheaper equipment. So it makes a lot of sense when you look at value engineering of equipment later on. Okay, 125. The overcap protection device, guys, the same calculation for overcap protection device. I take the 1.25, assuming it's continuous load, 83 amps, give me 104 amp, except I take it to 104. Where do we take it to find the overcap protection device sizes? 240.6, and the next standard 110, Chris? Yeah. 110 amp. Now 110 amp. Now here's my question for Rob. You go to Mashad Pooley, Rob, and you find that they actually size 100. They put this one 125 to match the panel, and they size the cable 125 amp. That's okay, as long as they size the cable to match the overcap protection device. So can I make this one 125? Yep. Can I make? But I have to make the panel match it now. The conductor match it. Okay. So the panel feeder, I say match the overcap protection device. So in my case here, if I'm to match the overcap protection device, I need to take 110 amp to table 310.15 B16 table, and that will get me 4 conductors. Why 4? I have a neutral now. And number 2, AWG. Check that one for me, will you? Can you check it's number 2? Number 2. Now, I can't emphasize, Dustin, you go to a company and say the overcap protection device, my panel has a juice of 125. I don't want to limit that juice to only 110. It might be actually a stupid idea. So I need to go put an overcap protection device 125 in it to match the buses. Great. Then what you need to do with the conductors, up your conductors, you're okay with that. This is okay. No problem with that. That's the test tomorrow, guys. Any question? Any comments? Any questions? straightforward. Just have all these rules written somewhere, guys, and good to go. Okay. Shall we give you a break, guys, and go break quick for lunch, and then after lunch I'll go over the theory. Cool. I need just 15 minutes or 10 minutes for the theory. That's all.